Now we get into the really, really good stuff. We get into normal distributions. Now, we can't just go calling everything that has a lump in it a normal distribution. But if there is reason for us to believe that it's normally distributed or approximately normally distributed, we can apply what's called the empirical rule to that. And it gives us a lot of information. If I give a test and the majority of the tests are C's, there are very few A's, there are very few F's, there are a medium amount of B's and D's, then perhaps the test scores were distributed normally. So we have this shape right here. Okay, and not such a good normal distribution, but it'll work. In the middle, if this is indeed a normal distribution, the mean, the median, and the mode would be right there, smack dab in the middle. Okay. If this is the mean, if I go out one standard deviation either side, and remember from the first video, the standard deviation is the average amount that the values vary from the average. So if we go out one standard deviation each way, then we have a whole lot of our data values. We'd have a lot of folks who were making the C's up to the B's down to the D's. In fact, we would have 34% of the values here and 34% of the values here approximately, and so that would be 68% total. This rule, known as the empirical rule, also has a name that just trips right off your tongue, the 68, 95, 99.7 rule. Those crazy statisticians. Okay, so what this means is if you go within 2 standard deviations either way from the mean, you gather up approximately 95% of your data values. Approximately 95% of the kids, if my data is distributed like this, are making somewhere between 2 standard deviations below to up to 2 standard deviations above. Ends up, believe it or not, being very useful information. So if I take the 68 from the 95, cut that in half, I get 13.5%. Now, it gets a little picky-ticky after this. Probably not used a whole lot, but then we go out to almost 100%, 99.7. And if we subtract the 95 from the 99.7, we get 4.7, we cut that in half, and we get 2.35%. Very, very few kids making this low of a score. Very, very few kids making this high of a score. Okay, what's left for the little dab that goes on this direction and on this direction? Well, 0.3% from 100 is what we have left. And so if we take that 0.3 and cut it in half, that is 0.15%, not 15%, 0.15% in each one of these little tiny pieces. In other words, very, very rare that we would be here, very, very rare that we would be here. Most of the kids are falling in here somewhere. All right. So if we look at how we're going to note this, I haven't talked about this yet. We're going to look at the mean. We're going to look at the standard deviation, and we're going to look at our notation for that. If it is for sure the real deal, mean, the for real average mile per gallon of Honda Civics. Yes, I have used this example many times before, former students. If it's the real deal, we denote that with Greek letters. and we use mu. If it is the real deal standard deviation, we use the lowercase s, which is sigma. If instead we have taken this from a sample, then it is known not in Greek letters, it's known in the Roman letters, which is our current alphabet. And so we are going to use the mean as x bar. Don't ask me why. And we're going to use s for the standard deviation and sample, and then that seems to make a little more sense. Okay, so Greek letters for the population numbers, Roman letters for the sample numbers. Things that come from the population, the real deal, are called the parameters. Things that come from a sample are called statistics. Now, isn't that convenient? S, S, T, T. All right. If I am looking back at this empirical rule, here's my mean right here. This is mean plus 1 standard deviation. This is mean plus 2 standard deviations. This is mean plus 3 standard deviations, and so on. Mean minus 1 standard deviation, minus 2, minus 3, and so on. Okay, so that's the notation. I love this stuff. Okay, suppose you could take a test in biology and you take a test in calculus. Let's say the biology test, you do know this. Let's say the test average was 73. You actually made a 78, and the standard deviation of the set is, this is a sample, is 8 points. Now, you were ahead of the group. This is a 100-point test. Now let's suppose that in your other class you made a 90. I'm sorry, the average was a 90. Average was a 90. Ooh, you made an 87. The standard deviation was a 3. It was 3 points. Now, I know on paper this score, 87, is higher than 78. But if what I want to know is how did you do relative to the whole group, compared to the whole group, we made a higher score here compared to the whole group because you made a score above average. Now, if you want to be able to give an actual identifier number for this, it's called a z-score. It's called a standardized score, and I've heard that the z-score comes from the z in standardized. Now, I don't know if that's true or not, but it's a good way to remember it. So here's how you get the z-score. The z is your value minus your mean. I always just say actual minus average over the standard deviation. So it would be what you got minus the average. We're above average, so that's going to be positive, over the standard deviation. And so what it will do is it will tell us we had a z-score of 5/8, which I believe is 0.625, and we'll hope that's it. We are above average. Not a whole standard deviation, but part of a standard deviation. On the other hand, over here, what we made, our actual minus our average over the standard deviation, is a negative now, and we made 1 standard deviation below average. So this is a way to compare how you did in one classes versus another relative to the group. Now I know you still would rather have the 87 than the 78. If your teacher ever gave back scores simply based on z-scores, you would be hoping that you had something positive. Although, as we can see, if it was negative, it still didn't mean that you made a bad score. It's all relative to the mean. That is how you do z-scores. Have a good day.